Hello and welcome back to this channel. Dear students, this is a quick revision session for application specific integrated circuits. So let us talk about the first part, that is ASIC design flow, application specific integrated circuit design flow and SPICE simulation. So from the exam point of view, you may expect the question like this: explain the application specific integrated circuit design flow. So this is the flow chart. First part is design entry. It's simple as the name indicates. We have to first enter the design details. You may use systematic entry, or you may use high level languages like VHDL or Verilog. Then next block is logic synthesis. As the name indicates, it contains the synthesis tools which gives the design description to the netlist. That means it converts the design descriptions, whatever you have entered, into the netlist, and the high level description is converted into simple logical blocks by using this logic synthesis. Then next is pre-layout simulation. So this block is basically simulator which is used to make certain corrections in the designing. Next is partitioning. You may also write this block as partitioning and floor planning. So in case of partitioning, as the name indicates, the entire system is divided or broken into number of smaller blocks. And in case of floor planning, this gives you the planning about the placing of blocks on the chip. Next block is placement and routing. So in this stage, the location of the cell in a block is decided, and certain connections between the cells and blocks are made. Next is the circuit extraction. We already discussed there is an effect of parasitic capacitance as well as parasitic resistance. So this circuit extractions determines the such parasitic effects. And last block is timing simulation. Actually, this block checks the functionality of the system as well as it gives the timing analysis. Next part is SPICE simulation. Basically, SPICE means simulation program with integrated circuit emphasis. As an example, we'll discuss how to do the SPICE simulation for AC analysis. We are considering a simple RC circuit which consists of one voltage source, DC voltage source V in, then resistor R1 whose value is 10 kilo ohm, and capacitor C1 whose value is 10 nanofarad. I have marked certain points in the circuit. This is point 1, this is point 2, and this is node or point 0. So this AC circuit analysis calculates the output variable as a function of frequency. The SPICE calculates the DC operating point and makes use of small signal model for the devices, all the devices, non-linear devices in the circuit. The output is usually in the form of transfer function of the circuit. Now about the SPICE code. Resistor R1 whose value is 10 kilo ohm is connected between 1 and 2. So I have written R1, 1, 2, 10K. 10K is its value. Same way capacitor C1 is connected between 2 and 0. So C1 to 0 value is 10 nanofarad. So 10N. V in is connected between 1 and 0. So V in 1, 0 DC, 0 AC 1. Then this command .ac DEC 510 10 mega. This .ac command informs the SPICE to run AC analysis at 5 points per decade. So this value indicates we have to perform the AC analysis at the rate 5 points per decade from 10 hertz to 10 megahertz. So this is the SPICE code for the AC analysis. Now there are certain components. Based on those components, these lambda rules are decided. So this is the list of components. First is substrate or well. Another name to the substrate is well. We know that in case of N MOSFET, P type substrate is used, and in case of P MOSFET, N type substrate is used. Then diffusion regions. These are the regions where the transistors are formed. These are also called active layers. So N plus is active layer in N MOSFET and P plus is for P MOSFET. Then polysilicon layers. These are used to form gate electrodes of the transistor. Next is metal interconnect layers. So these layers are used to provide the rails between power supply and ground as well as between input and output. Then next is contact and via layers. These are the layers used to form interlayer connectivity. That means to provide interlayer connections, these contact or via layers are used. Next most important part is MOSIC, that is MOS Implementation Service. These are scalable design rules. So we will talk about Lambda rules. So these are the rules. First is for N-well and P-well. That is N-type substrate and P-type substrate. We know that in case of N-MOSFET, P-type substrate is used, and in case of PMOS, N-type well or N-type substrate is used. So rules are minimum width is 10 lambda. Look at this diagram. So between two wells, minimum width of each well is 10 lambda. Then wells at same voltage level with spacing. Means if the wells are at same voltage levels, then the spacing between them is 6 lambda. So look at these wells. These are at same voltage level. So spacing is 6 lambda. Then wells of different types are spaced by 8 lambda. Next is rules for active area. Minimum width and minimum spacing. That means minimum width as well as minimum spacing should be 3 lambda. Then S or D, that is source and drain active to well edge distance or spacing is 5 lambda. SS means substrate or well contact active to well edge spacing is 3 lambda. Next is rules for polysilicon layer. So minimum width and minimum spacing is 3 lambda. Then minimum gate extension is 2 lambda. Minimum active area to poly layer is 3 lambda, and minimum poly layer to active area distance is 1 lambda. Then rules for making the contacts. So exact contact size is 2 lambda. Minimum spacing is again 2 lambda. Minimum spacing to the gate terminal of transistor is 2 lambda. Minimum allowed active overlap is 1 lambda. Then for metal 1, the rules are minimum width and as well as minimum spacing is 3 lambda. Minimum overlap of poly contact and active contact, that is contact of polysilicon layer and active contact, is 1 lambda. Then for metal 2, minimum size is 3 lambda and minimum spacing is 4 lambda. It is shown in this diagram. Then for metal 3, minimum width is 6 lambda and minimum spacing is 4 lambda. Then via 1, actually this via or contacts are used to make interconnections. So the rules are exact size is 2 lambda, minimum spacing 3 lambda, minimum spacing to the contact is equals to 2 lambda, and minimum overlap by metal 1 is 2 lambda. And last is contact to active area. Minimum active overlap that is allowed is 1 lambda, minimum contact spacing 2 lambda, and exact contact size is 2 lambda into 2 lambda. The next part is layout rules. There are 3 different layout rules. First is transistor rules. These rules are shown in this diagram. Actually, transistor is formed by making overlapping of polysilicon layer, I mean this layer, and substrate layer, P plus layer. This is the structure for PMOS transistor. So different rules are minimum length of transistor, which is same as minimum width of polysilicon layer, should be 0.24 micrometer, and width of transistor, which is same as minimum width of active layer, should be 0.3 micrometer. Second rule is contact or wire rule, which is explained in this diagram. Basically, contact or wire are used for making interconnection. Wire makes interconnection between two metals. Contact make interconnection between a metal and polysilicon layer. So it is formed by overlapping two interconnecting layers. It provides contact holes, which is filled with the metal between them. Third is well and substrate contact rule. There should be, proper connection. So this well and substrate should be connected to the supply voltage. If it is not connected, then the transistor contacts with the substrate will create the parasitic effect. Next part is design rule check, that is DRC. This comes under verification. Now, as I said, these are the computer-based rules. So it checks whether all the polygons and layer satisfies the specified manufacturing rules. It represents minimal set of rules, and those rules should be checked and if required should be corrected. Then the major drawback of such rules is that the design rule check is different for different manufacturers. So once you have designed or once you have finalized the design rules and accordingly the designing is performed, then porting is difficult. That means that particular design cannot be easily transferred to the another process. So porting of existing design becomes difficult. To avoid this, lambda rules are used. We have already studied lambda rules in detail, but for the lambda rules, again, there are certain disadvantages. First is linear scaling is possible only over limited range of dimensions. And second, these rules are conservative. So in industry, to avoid these disadvantages of lambda rule, micron rules are used. That means everything is expressed in terms of micron. So this is about the design rule check. Next is layout versus schematic. It is again used for verification purpose. So it is basically checking the connectivity of the designing. Schematic is basically a reference circuit. So the layout, the design layout is checked against the schematic and accordingly the corrections are done. It also checks, this stage also checks the electrical connectivity, that means input, output, then power signals are checked. It is also used to check the device size, that means length and width of the transistor or size of a capacitor, etc. Next is electrical rule check, that is ERC. As the name indicates, it is used to check the errors in connectivity or device connections. That means it is used for checking of floating nodes, then short circuit conditions and unconnected devices and so on. Next part is stick diagrams. Actually, every time it is not possible to draw the complicated original diagrams. So stick diagrams are used. Stick diagrams are the simplest diagrams. As the name indicates, this is a stick diagram which makes use of lines, or called, it is also called sticks, to represent the actual diagram. So you can say it is the simplified version of the actual diagram. Now let us learn how to draw the stick diagram. We'll consider an example of CMOS inverter. I have drawn the static CMOS diagram for this CMOS inverter. We know that inverter is a circuit in which output is you are getting output as a complement of input. We know how to draw such diagrams. The upper part is PVN, lower part is PDN. Upper part PVN is designed using PMOS. This is the PMOS, so I have marked a bubble over here. This part is NMOS. For the simplicity, I have marked source and drain terminal. Make it simple. For the upper portion, for the PMOS, source is at the upper side. So this source is connected to VDD. Remaining terminal is drain, from where you are taking the output. This terminal is gate. For NMOS, it is in reverse way. For the NMOS, lower part is source, upper part is drain. This is again gate terminal. Then a common input is applied to both PMOS and NMOS because this is the inverter. See, there are two transistors used in this case. How to draw the stick diagram? To draw every stick diagram, first step is you need to design the actual circuitry using CMOS logic. So this is the actual circuit of CMOS, of the inverter using CMOS. Now, after that, identify how many transistors are there. As shown in this diagram, there are two transistors. Then identify how many inputs are there. There is only one input, that is V in, and one output. Simply I have marked it as output. Now, how to draw the stick diagram? To draw the stick diagram, initially mark two horizontal lines. Upper horizontal line is VDD, lower horizontal line is ground. Then there are P MOSFET, two MOSFETs, P MOSFET and N MOSFET. So for P MOSFET, draw one horizontal line, call it as P diffusion layer. For N MOSFET, draw one horizontal line, name it as N diffusion layer. As we mentioned, there is only one input, so draw one polysilicon layer. So I will draw one polysilicon layer which is vertical. So I will write one polysilicon, I will draw one polysilicon layer vertically. Now, this is the polysilicon layer. Since there is one input, I have drawn one polysilicon layer. Observe this diagram. The drain terminal of PMOS and drain terminal of NMOS are connected together and from where output is taken. So I have to mark source and drain terminal for each transistor. Make the thing simple. Do remember like this. Whenever a polysilicon layer crosses the diffusion layer, it represents the transistor. So this is one transistor which is P MOSFET. This part is another transistor which is N MOSFET. I will write this terminal as drain terminal, this as source terminal. You may exchange the names. Similarly, this is drain for NMOS, this is source for NMOS. Now, as we discussed, drain terminals are connected and from where I am getting the output. So, I'll mark a cross here. I will take the connection. This represents the output. Same way, drain terminal of NMOS, I will mark a cross, right, like this. This is the cross sign. And from where I'm generating the output. Don't forget to mark this cross line because we are taking the connection from drain terminal of PMOS and drain terminal. This part is drain terminal of NMOS. This part is drain terminal of PMOS. So these two are combined and from where the output is generated. Source terminal of PMOS is connected to VDD. This portion is related to source terminal. So mark a cross and connect it to VDD. Again mark a cross over here for VDD. Then for lower portion, the source terminal of NMOS is connected to ground. So this part is lower terminal and this part is source side of NMOS. So mark a cross, join it to ground, again mark a cross. So this is the static diagram representation of CMOS inverter. Likewise, keeping in mind all these basic things, you can draw the static diagram of any CMOS logic circuit. Only the thing is that this circuit should be drawn properly without making any mistakes. Then using this techniques, whatever I explained right now, you can draw the diagram, static diagram, a stick diagram for any CMOS circuit. Now we will discuss important part of this chapter, that is design issues. So basically there are 4 design issues. First is antenna effect, which is also called plasma induced gate oxide damage. It is related to accumulation of charges on the conductor connected to the gate terminal. So there are many interconnected wires used in the circuit. So the interconnected wire which is getting connected to the gate terminal acts as an antenna, and this effect is called antenna effect. Usually a diode is formed between drain and source diffusion layers of the contacts. What is the effect of this particularly plasma induced gate oxide damage? So the first effect is the value of threshold level, that is VTH, is shifted. Then there is a degradation in the mobility, and it may happen that the failure of gate terminal takes place, as well as it will affect the current voltage IV characteristics of the device. Then how to reduce down this effect? This is basically related to the plasma processing. This plasma processing is used in the CMOS technology for etching and decomposition. So to reduce down this effect, reduce the built up charge by optimizing the plasma processing steps. That means we have to manage the plasma processing steps so that the built up charge will get reduced and this effect can be reduced. Then connect reverse bias diodes at the gate terminal. This reverse bias diode will not affect the normal performance of the structure, and use jumpers wherever it is possible instead of using a direct connection, because if you are using jumpers, then the length of the connecting wires gets reduced. Second effect is electromigration. This is the effect related to the current and current density, and because of which the heat is getting dissipated. So it is related to the movement of atoms based on the current flowing through the material. Usually high current flows for the longer time period. That means high current density is existing, and it will cause the more dissipation of the heat. Because of this heat dissipation, the transportation of metal ions takes place. Now it may cause the short circuit. SC stands for short circuit or breaking of wires in the metal layers. It depends on the temperature, which is increased due to high current flow, as well as current density and the crystal lattice structure. To avoid this effect, increase the metal width to reduce down the current density, then reduce the supply voltage, as well as you may reduce the frequency, supply frequency, and use short wires instead of using the longer wires. Next is the crosstalk effect. This term crosstalk is basically related to any unwanted transmission of signal through the coupling capacitor. As shown in this diagram, two wires are used. So wire 1 is related to capacitor C1. In the bracket I have written C1. Wire 2 is related to capacitor C2. This is capacitor C2. Now these two wires are the part of circuit, so they are connected by making use of a coupling capacitor. If you change the voltage related to wire 1 or voltage related to wire 2, then if any one of the voltage or if both the voltage are changes, there is effect on both the capacitors. Now because of this coupling capacitor which is connected between the two wires, the capacitive load of the circuit increases, which will reduce the speed of circuit. This effect is called the crosstalk effect. To avoid this crosstalk effect, the simplest technique is use the gap between these two. So if you increase the length of this line, I mean if you increase the gap between these two wires, then the effect of this coupling capacitor will get reduced. As well as another technique is make use of certain ground lines or VDD lines whenever required. So this is related to the crosstalk effect. The last effect is drain punch through. Actually, this is the effect due to the flow of current whenever the depletion region touch each other. So when the drain terminal has high voltage with respect to the source terminal, then the drain region may gets enter into the source region, and because of which flow of current takes place. This is the effect in which the breakdown takes place whenever drain body, dB stands for drain body, or SB, that is source body junctions, depletion region, I mean depletion region related to this drain body and source body junctions touch each other. As shown in this diagram, this is the depletion region related to source, this one is the depletion region related to drain. So they are touching with each other, because of which the breakdown takes place. There are two types. One is surface punch through. This is the effect, or the surface punch through takes place whenever the depletion region touch each other at the surface, and subsurface punch through whenever the depletion region are touching to each other below the surface. So this is about the drain punch through effect. So dear students, that's it for this quick revision session. So thank you. Thanks a lot for watching this video.